Okay, let's make a start. I'll chuck those in the chat. 2018 exam 1, and we hadn't quite finished question 7, but the remainder of that, there wasn't too much left to be talked about. Once you've done all the work towards finding the coordinates of P, doing the whole perpendicular line, finding the distance would just be a matter of just doing a distance formula from the origin to the point P that we would have found. In fact, I can even sort of just show that here. So the point P was 8/5, comma, -4/5. After you do that whole perpendicular thing to get there. That, or you might have already had a distance formula thing, which would have been the harder way to do it. If you already had it, then, well, then you're really happy because you just shove in the point and shove in the x value rather, and you're sorted. Either which way, you're going to get to the 4√5/5. But to start fresh, question 8. Show that f dash is equal to, well, that. Should be fairly chill. F of x is x squared e to the kx. We're just trying to do derivative. Yes, it's a show that, but I mean, it's tech free. It's whether it says show that or not is sort of whatever. I guess the only reason they've made it a show that is so that if you don't get the derivative right, you can then use the answer in part B anyway. First thing to always consider when doing derivative is what kind of rule are we going to use. Chain rule, product rule, quotient rule. And then from there we can be a lot more informed as to how we solve it.
Would we just use the product rule?
Product rule is correct. Yeah, absolutely. You got a multiplication of x squared and where is it? Yeah, the kx. And so yeah, your u is going to be x squared, your v is going to be e to the kx, and you go through the whole product rule thing there. Do you want to finish up the full product rule? Or you're happy enough with how that's going to work and eventually get to here?
Yeah, I'm happy.
Cool. Yeah, I don't. Did they give anything in particular? I guess all you would have had to do is do a bit of factorizing once you have your product rule, understanding that you need to make it look like exactly what they have there. But okay, part B, find the value of k for which f and f dash exactly intersect once. Yeah. You typically still try to rely on factorization where possible to make sure you don't lose like x equals 0 solutions when you do your division. The other thing, there's a couple of things that usually come up when you're trying to find one point of intersection. In the case of quadratics, you do stuff like discriminant. Discriminant equals 0 for one point of intersection. When it's non-quadratic, what you end up doing is usually trying to find making them tangent to each other at a particular point. But that usually happens more so with f and f inverse. I wonder if that's going to matter or not. But we do have to find where f and f dash are intersecting each other. So what's the most obvious direct approach to getting that at the very least?
Would we just make them equal each other and then?
Sounds appropriate to me. Make them equal to each other sounds like a great place to start. So we would go x squared e kx, that's our f of x, and then f dash is already given to us, x e kx, bracket kx plus 2. We're trying to find where they intersect each other, so I don't think I quite caught, which one are we solving for? a bit of a tricky question, actually, which variable we're trying to solve for.
The x?
Yeah, we're actually going to start by solving for x. And the reason why is because the whole reason we did this was to find point of intersection. It's only once we have x on its own that I reckon we'll be able to figure out what k value will force them to have exactly one point of intersection. So I think what's going to end up happening is we're going to get x on its own. You're going to have x equals something else. Both are going to have some k's in it, and we should be able to pick a value of k that will force them to be the same solution. Now, as I said before, try to work factorizing rather than anything else. Like, for instance, dividing both sides by e to the kx, usually not great because if there is an x solution in there, it gets disappeared. Same with dividing by x here, like cancelling out some x's, not necessarily recommended. So I'd start by getting everything on the same side. X squared ekx minus x ekx bracket kx plus 2 equals 0. From there, if we wanted to do some factorizing, what might we do? A few common factors in there we could factorize.
The e to the power of kx?
Yep, definitely one of them. So e to the kx can come out the front, leaving x squared minus x in that set of brackets. And then you've still got the kx plus 2 over here. There's further factorizing that can be done, but I guess we don't really need to go that much further because we've got a null factor law still. This times this equals 0. We've created our null factor law. Like, yes, you could take out another x out here, which you might end up doing anyway, but the point is when you're doing a factorizing approach, you want to get a null factor law, and we've achieved that. So we'll go term by term and figure out which of these is going to give us a solution of 0. So e to the kx, is there any value of x that would force that 0?
Would that be undefined?
E, is it undefined or do you just say no solution? I think you just sort of say no solution here. It means more or less effectively the same thing. It just means, hey, this doesn't contribute anything. Because any e to the kx could look like that or like that, depending on if k is positive or negative, both of which have asymptotes at 0. And so, since it never actually equals 0, yeah, I guess you could say it's undefined at y equals 0, rather than talking about from the perspective of x. Yeah, I don't think that's strictly wrong. But okay, so point is this one doesn't contribute any solutions. This one, so where does x squared minus x equal 0? That shouldn't be too bad. How would you go about that?
Do we factor the x out?
Yeah. X bracket x minus 1 equals 0, and this one should be chill. What are the solutions going to be there?
X equals 1 and 0?
Yeah, which is a bit concerning because now we've got, well, two solutions, and a k value isn't really going to fix any of those because there was no k involved here. That's a bit concerning. We'll keep going just in case. Kx plus 2 equals 0, and this one's just sort of whatever. X equals negative 2 on k. So these are all the possibilities. I would have expected these. These wouldn't have existed both. What's happened then? X squared to the kx is definitely f. f dash is definitely x e to the kx bracket kx plus 2. Getting them onto the same side. Yeah. And then chucking a minus on that one equals 0. Good. E to the kx out the front. X squared should be left behind. X should be left behind. Kx plus 2 should be left behind. Take 1. X equals 0, x equals 1, x equals negative 2 on k. Well, that's odd. Have exactly 1 point of intersection. X equals 0 or x equals 2 over 1 minus k. What do they have going on? And take x out the front as another common factor. Have a look at this version here. If I shove in x equals 1 here, does it work out? 1 minus... Huh. Oh, because there's no longer a multiply here. E to the kx comes out. Oh, yes, this is the issue. That's a full term, and then when I did this factorizing, I treated it as its own separate multiplication. This is not multiplying that. This is multiplying this one. Bad. That's what went wrong there. Okay. My bad. So if you have a look at the screen share version instead, they ended up dividing e to the kx, which you typically don't do, but because it had no solutions anyway, you can ignore it. And it makes it a lot more obvious how that now becomes what it should. You still get it over the same side. You take the x out as a common factor, giving it the x equals 0. And then you just got kx plus 2 for the... Oh, sorry, you get this solution from the last one. Yeah, that's what went wrong there. And then, the final thing you would do there is say, okay, x equals 0 is guaranteed. How do I make either this thing equal x equals 0 or just completely make it undefined to disappear it off? Both of those are acceptable approaches. There is no value of k that would force that second x solution to go to 0. And so the only other option you have is to make it undefined. So yeah, barring that little mistake on the factorizing there, that is still the correct approach there. Anything further to clarify on that? Cool. Let's see. G of x is equal to that. Diagram shows sections of f and g. A is the area. Describe just the shaded bit. Write down a definite interval that gives the value of a. That should be chill. We have the curve of f, we have the curve of g. Yeah, this shouldn't be so bad.
Would we just subtract f of x with g of x and do like the integral from 2 to 0?
2 to 0 and saying that f is on top of g, so top take bottom, f take g. Yeah, that's what it ends up being. Yeah. Because even if you do just area under f and the negative of the area under g, that is still the same thing. So yeah, 0 to 2, f take g, and then, well, yeah, that's what that ends up being. Nice. Using the result from part A, find the value of k such that a equals 16 on k. That should also, well, how complicated is this? You need to know how to anti-diff that. Really? Oh, using the result from part A. Yeah, okay. I thought it said using the result from C. Yeah, okay. So, you know, you've got f dash. You're trying to find an integral that would otherwise be super complicated. What are the sorts of things that are coming to mind based on those observations? So, we're in tech free. If we have a look at the integral that we were trying to accomplish, integral of x squared e to the kx, can't really do. That's a product of terms. Integral of, again, 2x e to the kx, again, a product of x and e to the kx. Can't really do integrals of products, at least not just by looking at a formula sheet. There's a specific sort of thing we have to follow to make it happen. I'm going to finish writing it out, and by then we'll see if you remember it. Okay, so this is the integration by recognition thing, which is if you have f and f dash, the relationship between them, then what you do is you make use of the fact that the integral of f dash is always f, and what you might notice is the similarity of the terms x squared ekx, x squared ekx, x ekx, x ekx. You'll notice there's a lot of symmetries involved in that. And so if we then, go ahead and make use of this, integral of this is equal to that, all we're going to do is try to rewrite the integral to make it look closer and closer to this, and then whatever's on the right-hand side will be what we ultimately want our capital F of x to be, the integral. Making sense? Does that ring a bell from what we've done previously? Cool. So let's do that. Integral of f dash. So integral of x e kx bracket kx plus 2 is equal to x squared e kx. Awesome. So we want to try and make this integral look a lot more like this one. What are some steps we could take to make that happen?
Could we take the 1 over k out?
1 over k. Oh, like over here. Yeah. Yeah, you can. So that would make it, you'd have, let's do over here. So you'd have 1 over k integral. Now, because this one doesn't have a 1 over k, you've got to put it into this now. So you're going to have k x squared ekx. Because now if you brought that 1 over k back in, that would now go back to that. And then, yeah, this one's now going to become 2x ekx. 2x ekx. Yeah, you can definitely work on this one and make it look more like this. It's a bit atypical to do that. Usually you do this one and try to make it more look like this. Though this is still a nice step to know to do anyway, because that is kind of important, because now you can see, oh yeah, I got a kx squared ekx, kx squared ekx. Huh, look at that. So knowing to do that is kind of helpful. What can we do here? Because we can rearrange this all we like, but because it's not really in an equation, it's kind of hard to really make use of the result, like know exactly what you're doing with the result there. Whereas on this side, it's fairly obvious because, hey, I got this integral, it equals that, so when I look at this, I just replace it with that. Versus this, there's no actual equal sign here. It's a little bit harder to work with. Not impossible, you can definitely do it, but a bit harder. So as far as rearranging this a little bit, how do we make it look more like that, or more like this one that we just made over here? Got a set of brackets. There's no brackets in either of these on the top. What could we do to get rid of those brackets?
Do we square root?
Would quite be well, as in square root because of over here, the x squared. It wouldn't quite be that. I'd be more focused on trying to make the left-hand side look more like this here. And what I'm noticing here is that none of these have brackets in them, right? Like you got two terms separated by a plus, you got two terms separated by a plus. This doesn't have that. I mean, it kind of does with the plus here, but there's also bracketed terms in there. So rather than square rooting, which would be really painful to work with, you square root that whole thing, square root this. I'd rather be focusing on maybe expanding these brackets out so it looks a little bit closer. So you're going to have kx and x, so kx squared ekx, and then 2x ekx. And that's, well, we've done nothing that requires anything on the right hand side, so we keep that as is. And if we do a bit of a comparison, I don't know how good that's going to show up readability wise, but x squared ekx, kx squared ekx, kx squared ekx, 2x ekx, 2x ekx. Yes, there's a 1 over k involved in here that we don't have over here. So if I were to introduce a 1 over k into this equation, how could I potentially do it? This is one of the weirder ones. It's a bit less common to have to do this. In fact, no, I guess we don't even really need to. If you don't, I mean, maybe try to answer it anyway, but you don't actually necessarily need to know how to do that. I'll give you like a minute or so to think about it. Or just let me know if you want to move on. One of the two. If you wanted to introduce a 1 over k, or pretty much anything, into an equation, you basically just got to do it to both sides of the equation. So if I want to put a 1 over k here, I have to also multiply this one by 1 over k. That's all that was. That is a bit weird to introduce a variable that doesn't already exist in here. Like, we're very used to saying, oh, there's an x squared over here, I can divide by x squared. But realistically, you can actually do that with anything that you ever want. You don't have to just use what's in front of you. You can introduce things from, well, from anywhere, just for the hell of it, as long as you do it via the laws of algebra, maintaining the equation on both sides. But what I meant was you actually don't even have to really do that, because, hey, you've got this integral, you've got this integral, this is just that. In fact, you can even, probably an even easier way of going about it would be to say, hey look, 1 over k times that is what we're trying to find. We have, well, just that. So instead of saying we have our f of x, capital F of x is equal to this thing, it's 1 over k, f of x is equal to 1 over k times that. So basically you're going to have your 1 over k x squared ekx, because this antidiff of this is that. You're just going to introduce those 1 over k's like we said. And yeah, with that in mind, since we got our capital F of x like we want, yeah, is that. It's a bit cheeky there, because the 1 over k is outside the integral, so calling this capital F of x is a little bit strange. Yeah, you might not want to do that and just hold off on it until later, because this and this are exactly the same. You ignore the 1 over k for now. We want 1 over k times that, but we'll settle for just doing this thing, the capital F of 2 minus capital F of 0, and then introducing the 1 over k later. That's probably a bit more appropriate, just based on the definitions of things, to make it less complicated, I'd say. Capital F of 2, capital F 0, what did I say, equals, minus capital F 0. That's all we wanted, right? It's just find the value of k such that capital A is 16 on k. This is, or at least part of that. So we're going to have 2 squared, so 4 e to the k times 2, and then, well, just 0. So that's the capital F of 2 minus capital F of 0. That's that part of the integral. We can introduce the 1 over k bit, because we need that. 1 over k needs to come in there. And because this is an area equation, it equals area, but we're told area is 16 on k for this thing. K's cancel. 4e2k equals 16. e2k is 4, and well, just logs here. Natural log 4 is equal to 2k, k equals half natural log 4. You can put this in here as a root thing, basically, so k equals natural log 2, just using the log law thing of coefficient at the front comes in as a power. So that's probably the simplest form you can write that in. Bit of a ride there. Is it fair enough up until that point? I'll recap it, but is there anything you immediately seeing that you want me to clarify?
No, it's all good.
That's all good? Okay. So just to recap why we're even doing this in the first place. Using results from part A tells us that that whole diff and f of x relationship is going to be important. we've got f dash, and we've got an integral that we can't normally solve. That's when we do this sort of thing. So always, always, always starts with integral of f dash is equal to f. That always happens. And then from there, you're just taking the integral term that you have and then rearranging it into the integral term that you want. Now in this case we did a bit of back and forth to try and do a bit of rearranging here and then do a bit of rearranging here. It's usually that you focus all your effort on this, but this actually did need to happen at some point, so whether we did it at the start or the end was whatever. And then yeah, once you have that, you have your antidiff, and the rest is stuff you already know how to do, just solving a definite integral. In this case we had a value that we were targeting, so we could figure out what the definite integral is supposed to be, and then solve for k from there. Oh, question 9, more definite integrals. Pleasant. This was definitely a weirder one. This was my exam, by the way, that I graduated on. I'm not 100% sure that I would have done particularly well on this one, at least at the time. I should be fine with it now. I guess I'll find out. We have the graph of x sine x here. We're told the integral of x sine x already off rip, because otherwise we wouldn't really be able to find it. And then based on that, evaluate this, where n is even or 0. Because this is evaluate, we're just going to try and simplify it all the way down. So I'll give you a moment to have a think. How might we start it out? Ultimately it just says evaluate this, which is a definite integral. So a good place to start would be to do the same thing we do to evaluate any definite integral. What sorts of things I do want to do? We've had some practice evaluating definite integrals today already. What are the steps, just broadly speaking, for any basic, like I want to integrate little f of x, ignore what any of this says. I'm just trying to do integral of some function f. In fact, let's even give an example, x squared plus 1. What are we going to do to evaluate this definite integral?
Anti-diffing and then subbing in.
Yeah, antidiff and sub in. So we're going to do exactly the same over here. We need to antidiff x sine x. Normally quite tough, but we have a bit of help here. What's the antidiff of x sine x?
Sine x minus cos x plus c.
Yeah, that's the one. So our capital F of x, in this case, the antidiff is going to be our sine x minus x cos x from the given antidiff there. What did you say the next step was going to be?
Subbing in the bottom and the top.
That's it. So we want to be doing capital F of bracket n plus 1, well, double bracket actually, n plus 1 pi, that's the top, minus capital F of bottom, which is just n pi. Let's see how we go. So sine of n plus 1 pi minus bracket n plus 1 pi cos n plus 1 pi. So that's the first term there. I should probably make that n pi plus pi. Make that a lot easier. I'll do that in the next line. And then minus capital F of n pi, so using big brackets for that. So sine n pi minus n pi cos n pi. Minus n pi cos n pi. Brilliant. Love that. They did give us clarification around n. So n has to be even or 0. N is even slash or 0. Right. Don't have to be too specific with the notation there, just a reminder for ourselves. Let's make this not look like shit. So we're going to have sine, just going to focus. There we go. Expanding that out, you're going to have n pi plus pi minus, yeah, I guess we kind of have to leave that like that, n pi plus pi cos n pi plus pi minus sine n pi minus n pi cos n pi. From here we can't do a whole lot algebra-wise, because the brackets of the cosines and sines aren't the same. There's no like immediate obvious algebra simplifications to be done here. So we got to make use of the fact that n is even, and whenever you're dealing with weird circular function stuff, there's going to be some symmetries that you could make use of. These brackets are a bit bigger and scarier. You probably want to start with these. So sine n pi, where n is either even or 0. Let's do some testing. 2 pi, 4 pi, 6 pi, or 0. If I shove any of these into sine, what's that going to become? Yeah, because that's what the brackets are going to end up looking like.
Would it just be 0?
Yeah, that's it. So any even n is going to result in, like, any of these, and, you could go on forever. Always ends up being 0. So that term goes to 0. Nice. How about this one here? Cos n pi. So it's the exact same thing. You're either going to have a 0 in the brackets, 2 pi, 4 pi, so on and so forth. It's the exact same spot. What does cos n pi always come out to be? We won't worry about this bit for now.
1.
That's it. Yeah, so that's always 1. So this term always becomes 1. So this whole set of brackets is now just negative bracket negative n pi times 1. So just n pi. The 1, negative, negative is positive, and then that's just the 0. That whole thing disappeared. Yay us. Same thing over here. So n pi plus pi. So now if n is 0, you're going to have pi. If n is 2, you're going to have 3 pi. So basically all the odds in sine now. What's going on there?
It would be 0?
Yeah, still 0. That's it. It's that one. 0. Exact same thing over here. So cos for all the odds. What's that always going to be?
One.
Negative 1. Because you're on the left hand side of the unit circle. You're over here. And so yeah, negative 1. Which means this negative is going to flip to being a positive, and so in reality that's gone. Positive n pi plus pi, so n pi plus pi, and then, well, you got another n pi over here, 2n pi plus pi, and if you want, you can take a common factor out, pi bracket 2n plus 1. And that would be the evaluation. So we went from that to this, just by using trig stuff. Making no sense. I think as far as trig stuff goes, the symmetries, this is probably on the easier of the symmetries, because you're just doing the quadrant boundaries. But let me know. Anything in there that was weird? Beyond the fact that it's a weird question in general. Because we're going to do the exact same thing for double I, but odds this time. In fact, do we have any other questions in this? We do. I might just leave that one because it's the exact same thing. You can see it's the exact same function that's anti-diffed over the exact same domain. But this time you're going to be putting the odds where there were evens and evens where there were odds. I wonder if they've got a set of solutions for it. Yeah, okay, they didn't bother either. Said the same thing that I said, which is forget it, just do the same thing as before. Yeah. That's pretty much it. Do you want to see another run through of that, or are you happy enough with how it's going to work?
All good.
Nice. Okay, find tangent to x sine x at that point. That's going to be chill. Wait, maybe. Oh yeah, because tangent is diff. We can diff this, that's fine. Yeah. Solving tangents, what do we got to do?
Would we find the derivative?
Derivative is going to be one point that needs to happen, yeah. We've done a similar thing already. This is just going to be your product rule. U equals x, v equals sine x, u dash is 1, v dash is cos, y dash x cos x plus sine x. Yep. Diff is important there. What else do I need for tangents?
The coordinates.
Yep, so we got those. We got the x and y, which is nice. Only one thing that's missing left. To create any linear tangent, y equals mx plus c.
Do we sub in the x into the derivative that we found?
That's it. And what's that going to find for us?
The slope?
Yeah, that's it. Gradient. Yep, so negative 5 pi on 2 cos negative 5 pi on 2 plus sine negative 5 pi on 2. This requires your unit circle ability. Negative 5 pi over 2, so, you know, negative 4 pi over 2 puts you here. Negative 5 pi over 2 would then put you there. So, yeah. Going to have gradient equals, so cos of that spot is 0, so that whole thing disappears. Sine of that spot is negative 1, so yeah. I guess it's just gradient negative 1. Nice. Gradient negative 1, point as given. How do we put it all together?
Y equals minus x.
Yeah. Y equals minus x plus c. And then finally,
We find c.
yeah. So we're just going to sub in that point, find c. And they might have work solutions for it, and not particularly. But yes, you do just plug in that point. X is negative 5 pi on 2, y is going to be the 5 pi on 2. That's going to get you... Oh, so it does actually just become y equals negative x, because they cancel down. The c goes to 0. Easy. Yeah. Nice. So, transformation, cool, let me fix that one up for you. X dash equals x plus a, y dash equals y. So that's being applied to x sine x, and it's making it look like 3 pi x sine x. So this is going to convert x sine x to 3 pi minus x sine x. And that's a bit cheeky actually, because anyway, it's a one marker. They don't give you that much room for working out. It's one of those things where you could probably take a shot in the dark and get it decently right. Or you could go out of your way to do the whole application of the transformation, which is a lot more safer, probably. Might not even be that much safer, because you still got to use the trig identity afterwards. Nah, in both cases you still got to do a trig identity. If you were to take a shot in the dark at it, what do you think A is likely to be? Or at least be close to? Just based on how one is being mapped onto the other.
I think I would just say like 3 pi.
Yeah, that's right. So it's either going to be plus or minus 3 pi, depending on the weirdness of how things get flipped and shit. But yeah, I mean look, A is a horizontal translation. That's going in the spot where you would expect a horizontal translation. Now you'd also expect it over here, so that's a bit weird, right? Why is it not over here? That's going to come with the trig stuff, which is why I feel like probably applying the transformation is best, so you can see exactly how the trig stuff works. So to apply this, you'd flip this over, so you're going to end up with x equals x dash minus a, and then you shove it into this one, so you're going to have x minus a sine x minus a, and you want it to look like this. Now the first thing we need to be able to do is figure out how can I rewrite x minus a as just x in here. What kinds of trig identities do I know of that can achieve that? So what I'll do for that is I'll pull up the, unless you already know it by the time I pull it up, I'll pull up all the different trig identities that exist, and we'll see which one we can apply. Alright, that's as a screen share there. We're looking to figure out which ones of these start with a sign x plus or minus a thing, and then go back to being regular sign. And we'll figure out which of those we could now use. Just for indexing, we'll say it goes left to right, so this would be 1, this would be 2, this would be 1, 2, 3, 4, 5, 6 of the half period, so on and so forth. Just so you can index it properly. We want to go from x minus something to just regular old x, specifically in sign. Now that can be still a bit nasty, because x is theta in this case, if you're comparing 1 to 1. So maybe, to make it a bit easier, because what you'll notice is that probably the ones you'd be looking at would be these up here. You got sine pi plus x or pi minus x, one of the two. You know, something plus or minus, and it goes back to being just the x in the brackets or just the theta in the brackets. But the problem is the plus slash minus is on the x, not on the a, or in obviously the formula sheet thing has pi there. So one of the things you can do there is, yeah, you can take a negative out. So take a negative out of it, gives you now a minus x in there. I'm debating whether or not to do that, simply because it kind of even makes it look a bit tougher. So to do a further layer of abstraction, I'm going to take this thing in the brackets here, we can ignore it for now, and then just do this. So we now have the x minus a from before, the sine, and the negative u in there. So to recap, the reason why I've done that is because I want to make it look closer to what we have in those half period formulas, where it's thing, the constant, plus or minus the variable, rather than the other way around, which we had here. But that created a new complication, which is that we now have a negative chilling there. So we've got to handle that one first. That would bring us to the reflection properties, which is sine of negative theta is always just negative sine of theta. I have that one highlighted if you want to have a look at the screen share. And so fundamentally it just means we can go, oh, cool. This negative can now come at the front, negative bracket x minus a, and this sign can go right back to being positive in the bracket. U is still a minus x. So we do that. Sine of a minus x. And sine of a minus x is this one that's highlighted on the screen share. Pi minus theta, a minus x, where a is pi and minus theta is your minus x there. And so, yeah, hang on a minute, is that going to work? Because if you take a as pi, oh yeah, it's the same. So if you take a as pi, the symmetry thing will still work. the challenge here is that you want it to have 3 pi in there. The thing to recognize there, I believe, would be as follows. So, you've got your unit circle, you've got sine of theta's over there, pi minus theta would put it there. 3 pi minus theta. This is also 3 pi. Yeah, any odd pi is there. Okay, so it does end up being the same thing. So choosing A as 3 pi here cancels that bit out. Sine of x. Then you have negative x minus 3 pi. Bring the negative through. Oh, whoops. 3 pi minus x sine x, which is what we wanted. So that's a whole long proof to show how to go from one to the other. You don't need nearly that much to prove it, which is why I sort of started off by saying if you were to take a shot in the dark, what would it be? Probably 3 pi. The only problem there, of course, is there was probably a risk that it could have been negative 3 pi instead. Yeah, so if you have a look at the 9C as the screen share, it was a 34% pass rate because people took a shot in the dark at A equals 3 pi. More people chose negative 3 pi. So, you know, on average you get the mark about 34% of the time if you take a stab at it. Alternatively, you do all the bullshit that I just did to to prove exactly which one you want to have happen. I take it there's plenty of questions there, but it's probably not one you should dwell on too much. Happy to clarify though if you want me to clarify any bits of that. That, or you can just enjoy the ride that was me going through a bunch of trig identity stuff, which we had to do a couple of actually. One trig identity here, the other trig identity stuff over here. I guess that's less identity and more just knowing that sine and cos at particular spots are what they are. Cool. I mean that... Ah, there is one more question. Damn it! It's alright, we'll start fresh next time. Cool. If there's anything further you'd like me to clarify, happy to do so. Otherwise, yeah. 2 more lessons for you, pretty much, right? And then you got the exam, Wednesday, Thursday.
Yep.
Exciting. Alright, keep me posted if you have any questions that come up. Otherwise, yeah, I'll leave you to it.
Thank you.
No worries.